Hi, my name's Will Krawczyk, Scientific Services Manager at Chemical Computing Group. Today I'd like to introduce homology modeling in MOE. In this demo we're going to start with the sequence before building a structural model, and then finally we'll analyse the quality of that model. This is a typical workflow for cases where no crystal structure exists. So I'm just going to go ahead and grab the sequence that we'll be modelling. And MOE will auto-detect that this is a sequence, and therefore it opens directly in the Sequence Editor, our launching point to the various protein modelling tools that we have in MOE, including the Homology Modeler. Before I do that though, I'm just going to wrap our sequence and switch to the single letter code, and then I'll move on to the first step of homology modelling, which is to find the template that we'll use to build our model. So for that, I'm going to search MOE's clustered family library that contains PDB structures. There are two parts to the panel. The top allows us to specify the query. Results will be written to the bottom. So MOE has detected that we have a sequence loaded, so I'll just bring this into the panel. I could equally copy and paste it before I hit search. And now MOE will search the non-redundant protein domains from the protein data bank. This is a database that contains over 40,000 structures, clustered by proteins that have similar domains and sequence similarity. The templates that match our query get displayed in the lower portion of the panel. These potential templates are ranked by the hidden Markov model E-value, whereby the lower the score, the better. So I'm just going to go ahead and take the first entry, that with the best score, and I'll click Load Alignment so that I can view this pre-aligned family with the chains sorted by sequence similarity to the query. Now, I could manually inspect them here, but I want to send them to the sequence editor for that task. I'll first, though, just toggle on Load Query Sequence so that my query sequence is aligned to that of the templates. With that, I can now close the PDB search, and since I aligned the query, I can then remove the original query which is not aligned to that of the templates. Now, in this particular case, we're actually modeling, building a model for which a structure already exists in the PDB. In real life, this typically doesn't happen because if we have a resolved structure, we don't need to do homology modeling. So I'm just going to remove this chain also so that it can't be used in the generation of our model, but I will bring it back later for validation. So next, let's analyze the remaining templates so that we can find the best one to build our model. And for that, I'm going to use the Similarity Monitor, which calculates all against all sequence identity, similarity, and RMSD distance matrices, displayed either as a color-coded heat map or a tree, both of which can be exported or written to a text file. Using the plot to look at the pairwise identities of the chains, I'm looking for structures that have the highest percent identity to that first chain, the query. And this would suggest that it's actually the first three that are the best. I can also do this using the dendrogram directly in the sequence editor. I can use this to look at identity or similarity, and here we're looking at similarity. I'm just going to sort the chains to ensure that there's no overlap in the dendrogram, and note that when I hover over the branches, I get a readout here on the footer displaying the similarity. So again, this is confirming that it's the first three templates that are best. So for that reason, I'll delete everything else and just remove these so that we can continue working on those first three templates. Now that I've deleted some of those templates, I can realign the sequences so that we get an optimal alignment. For that, I'll use the Align Superpose button, and this opens the panel on the footer. There are three parts to this. The first Setup Chains button allows us to control blocks for group-to-group alignments and handle multimeric structures. Middle part is for aligning sequences, and the third section for structural superposition. So here I'll simply click Align, and when I do that I just notice we've got some insertions and deletions. So in this case we've got extra residues present in the query relative to the template. In any case, the homology modeling application is going to be using the backbone geometry from the template, and in regions where there are indels, MOE will be using the loop modeler by default. Since multiple models will be generated and written to the database along with scores, we can later analyze these models to select the most appropriate. So let's go ahead and launch the homology panel, for which there are three sections. At the top, we can select the sequence we want to model and the templates that will be used. The middle allows us to control more advanced features such as loop generation, and the bottom for refinement and scoring. So MOE has automatically detected the query sequence, and next I can select which template to use. Template 2 has been selected for the first chain that has atom coordinates, and this happens to be the one that we earlier identified as being the best template in terms of percent identity and similarity, so I'm not going to make any changes here. What I will do though is just change the number of main chain models that we'll be making. The default is 10, I'm just going to switch this to 5. And I'll just note here also that we can also specify the number of sidechain models to build for every main chain model, with the option to specify the temperature in Kelvin. So I'll just go ahead and click Build. A database viewer is opened where the results will be written. I just want to show some additional features and options when it comes to homology modeling. So here you'll notice that we have some empty drop-downs. This is used for when we want to model a multimer, which we're not doing today, hence why I didn't use them. In terms of the options, we have the Used as Environment option, which would allow us to specify ligand atoms. This is useful when we're building a model and we want to preserve a binding pocket, for example. Template override is useful in two use cases. The first would be when the primary template is missing a specific loop or region and we want to graft it in from a secondary template, or perhaps we want to consider different conformations using a secondary template. If I just take a look at our sequence, I can see here template 2 is being used, but it's missing some residues here. However, those residues are present in templates 3 and 4. And looking at the similarity to the query, it would look as if template 4 is going to be best. So what I could do here is I could just use the selected residues from template 4 and override chain 2 in that region only, grafting that loop onto the main template. Results are written to the database viewer, which has a look and feel like an Excel spreadsheet, but actually contains the wire structure of our generated models. The models are ranked according to their GBVI score, whereby the more negative, the better. By default, 10 independent intermediate models will be built. Today we're just doing 5, and these different homology models are the result of the different loop candidates and sidechain rotamers. The intermediate model that scores the best according to the chosen scoring function is used as our final model. It's labeled finalized and refined using the refinement settings defined at the bottom of the homology modeling panel. So I'm just going to send our final model to the main MOE window with a double click, and I'll click yes to clear the system, and then just click center, and our homology model now appears in the main MOE window. Next, let's assess the quality of that structure, and I'll do that using the geometry checks, and you'll see here a variety of checks that can be performed. I'll just click that first one, the phi-psi plot, whereby at the top we can specify which residues we want to include in the check. We can select what check we want to perform. The middle displays the results, and we get a key at the bottom to interpret the plot. So here we can use the Ramachandran plot to identify any outliers. We can also change, so we could have a look at perhaps bond lengths where we're looking for any of these data points that fall above the dotted line. In this case we don't have any, but some get quite close. Now in this particular case we have we're modeling a protein for which we already have a resolved crystal structure. So let's have a look at how these two compare. I'll just go and grab that from our sample mol directory and bring that into the main MOE window. I'll color according to chain. I'll display the ribbon. I'll hide all of the atoms, and next what I'll do is just bring those into the same frame of reference, doing the alignment and then the superposition. Let's just send to the view, and we can see that we have pretty good correlation between the model and the resolved crystal structure. As expected, there are minor differences in terms of the loop regions, but overall we have pretty good correlation. I could also investigate different conformations of the loops for those intermediate models, so let's just have a look at that. I'll bring those into the main MOE window, and this time what I'll do is I'll color all of these green apart from our resolved crystal structure that I'll colour in magenta. So here we can have a look at some of the different conformations that are possible in these loop regions. And with that, it brings us to the end of today's session, where we generated a structural model directly from Sequence using the Homology Modeler. We also analysed candidate templates within the Sequence Editor and using the Similarity Monitor, before assessing the quality of the final model using protein geometries. If you have any questions, please do reach out to us at support@chemcomp.com.